Today we will discuss about threaded binary tree. So this threaded binary tree can also be called as TBT, that is threaded binary tree. So consider this is a given binary tree. So this is a simple binary tree, and normally while coding the node structure for this tree is declared like this: struct node. In that node there will be total 3 fields. One will be for storing data. Data can be of any type, either integer, character, or float. So here we are considering integer data. And then apart from this data field, there will be two more field. So one will be a field which is struct node pointer left child. So this is the field which will hold the address of left child of that node, and another field is struct node pointer right child. So this field will hold the address of right child of the node. So the same tree, if you want to visualize in terms of node format, where each node has minimum 3 fields, one data and two pointer fields. So it will look like this. The same tree will look like this. So here A is a data, then left child pointer right child. So left child pointer is holding the memory address for node B, and right child pointer is holding memory address for node C. Similarly, for node B also there is one left child field and one pointer, right pointer, which is holding address of right child. So similarly, these are the different nodes, and this is how we normally represent on paper. But actually in node structure format, your same tree will look like this. So why we are going to study a threaded binary tree? What is the significance of using threaded binary tree? So as you see here in this node structure, here it is holding this left child pointer is holding address of node B, right child pointer is holding address of node C. Similarly here left child pointer holding address of D, right child is holding address of E. But if you look at this node H, there is no node attached, or there is no left child attached to this node H. So definitely its left child is holding null. Similarly, it doesn't have any right child, so it is not storing any address of its right child. So again, the right child pointer field is holding null. Similarly, for I node, again it is null. Right is also null. For node E also, it doesn't have any further nodes attached to it, so its left and right field, right pointer field, will be storing value null. Null means it is not holding any memory address. So similarly for this, but it has one right child but no left child. That's why left child pointer field is holding null. For J, it doesn't have any further left or right child, so both the links will hold null value. So this is how it is given. Now, if you consider this tree, now what is the purpose of using this threaded binary tree? So in a linked representation of a binary tree, the number of null links or the number of null pointers are actually more than that of non-null pointers. So if you consider this tree, this given tree, so again it is a binary tree. Here we are representing it in terms of simple node structure. So here the left field will hold address of node D. For D there is no further node, so D is pointing to null. Again for node E, left and right are pointing to null. For node F also left and right are pointing to null. Similarly for node C, There is no right child present. That's why it is null. That is, it is not having any right child. So if you just look at this tree, so total number of links. So if you see this statement, the number of null links are more than non-null links. So this is a link, the left child pointer link, which is now here in this representation is replaced with this age. Right child pointer link for A is replaced with this age, which is connecting to right child. So here these are the useful links which are actually holding address of some node. So how many in this representation, tree representation, how many actual useful links are used? If you count it, it is 1, 2, 3, 4 and 5. Total 5 useful links are here, and if you want to count the links which are not useful, the links which are holding null value, so that is 1, 2, 3, 4, 5, 6 and 7. So here it proves the statement that in the link representation of binary tree, the number of null links are more than non-null links. So for the same tree representation, n is the number of nodes and that is 6. So total number of nodes are 1, 2, 3, 4, 5 and 6. So total nodes which are holding some data is 6. And number of non-null links is given by formula n minus 1 that we already saw. And we have counted here also 1, 2, 3, 4 and 5. So these are the number of non-null links, or you can say these are the number of useful links. And the total number of links are given by the formula 2n, where n is the total number of nodes. So total number of links for this tree is equal to 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 and 12. So total number of null links can be counted by this formula, total number of links minus total number of useful links. That will give you total number of non-useful or the links which are holding only null pointers. And that comes out to be 7. So here 7 non-useful links are used, whereas useful links are only 6. So ultimately what we are doing here, this memory which is supposed to hold the address of its left child is actually not holding any address. It is storing null value. So lots of memory is wasted in just storing the null value instead of storing any useful data. So in threaded binary tree, we are going to make use of all these fields which are now holding null value. Instead of this null value, we will make them to store some useful value, that is to store some nodes address. So what address they will be storing, that we will see with some algorithm. So the objective here is to make effective use of these null links or null pointers. So according to this idea, we are going to replace all these null pointers by appropriate pointer values, and that pointer values will be called as threads. So all these null fields or all these pointer fields which are holding null value will store some address value, but that address value will be called as thread. And a binary tree with such pointers are called as threaded binary tree. So again, threaded binary tree is a kind of binary tree where these null links or these null values will be replaced with some threads. So if it is replaced with some thread, it becomes threaded binary tree. In the memory representation of a threaded binary tree, it is necessary to distinguish between normal pointer and a thread. So definitely Here your node will have different fields. One will be storing data, another will be holding address of a child, and one will be field which will be a thread field. So we need to distinguish between these fields, which one is thread and which one is normal pointer. That means which one is the pointer storing the address of a child node. So any given binary tree can be converted into a threaded binary tree. For that, we have to keep these 2 points in a mind. So first point is we need to keep the leftmost and the rightmost null pointer as null, or we can say a dangling pointer. So if you look at this diagram, so this is the leftmost null pointer and this is the rightmost null pointer. Or if you just look at the previous diagram, here all these blank fields are holding null value, right? So here out of all these null, which one is the leftmost null? This will be the leftmost null value. And which one is the rightmost? This will be the rightmost null field. So this leftmost and rightmost null field will be will remain null only, or you can say it will be a dangling pointer. So keep the leftmost and rightmost null pointer as null or dangling. So here it is represented as dangling because it is not pointing to anything. They are just kept like this. So it is a dangling pointer. Second rule is change all other null pointers as. So we have 2 options for null pointer. Sometimes the left field is null, sometimes right field is null, or sometimes both left and right field are null. So in that case, the left pointer will be replaced with Inorder predecessor. Right pointer will be replaced with Inorder successor of that node. So just look at this tree. First of all, we need to find out the in-order sequence or in-order traversal sequence of this given tree. Starting from the root A, first for in-order traversal, what is the sequence? First, we need to visit the left node, then second root node, and third we will visit the right node or a right child. So if you start from A has left B, B has left D, and D has left node H. So H is the leftmost node of this tree. So H will be printed first. Then after that, after left child, second preference goes to the root. So H has D as a root, so D will be displayed. After that, third preference goes to right child. So D has I as a right child, so I will be printed here. So again, it will go back to its previous node. Left side for this node B is already visited. So now it's turn for a root node. So B will be displayed. Then third preference goes to right child. So B has E as right child. So E will be displayed. Now for node A, all the nodes on the left side are visited. So preference 1 is over. Second preference goes to root itself. So A will be displayed here. After root, third preference goes to right. So in right, again we have a subtree. If you come at C, C has a left child F. So F, then root is C and right is G. So this is the in-order traversal sequence for a given tree. So as the rule number says, keep leftmost and rightmost null pointer as null or dangling. So H is H, left field is the leftmost pointer, and G's right field is the rightmost pointer. Now they are kept as null or a dangling. Second rule says change all other remaining null pointer as if that is left null pointer will be replaced with in order predecessor of that node. Now I has I doesn't have any left child, so its left field is null. So left field should be replaced with inorder predecessor. So here in inorder sequence, if you see I has predecessor D. So I left field which was null, now it will be storing address of its predecessor, that is node D. So instead of storing null, now it will store address of its predecessor. Now for node I, right field is also null because it doesn't have right child also. So right null pointer will be replaced with inorder successor of that node. So for node I here in inorder sequence, node B is the successor of the node I. So the right field of I will hold address of its successor node, that is node B, instead of null. Similarly, if you look at node E, again node E doesn't have any left or right child. So left pointer field which was storing null will be replaced with inorder predecessor of E. So for E, predecessor is node B. So E will point back to B, or E will store the address of node B. And right child, sorry, right child will hold the address of inorder successor of E. So who is inorder successor of E? Node A is the inorder successor of node E. Successor means the node which comes after that node. So for node E, node A is the inorder successor. So right field of this node will hold address of node A instead of null. Similarly for all other nodes. Now here you might be confused why we are keeping the leftmost field and the rightmost null field as dangling or null. Because by the rule that left field should store the inorder predecessor of that node. So if you look at node H, it doesn't have any node before it. So it doesn't have any inorder predecessor. So that is again null. That's why it is dangling. So similarly for node G, there is, as the rule says, the right null pointer field should store the address of inorder successor of that node. Now for node G, there is no further node, that is it doesn't have any inorder successor node. That's why the field is null or it is dangling. So this is how we can convert a given binary tree into a threaded binary tree. Now in threaded binary tree representation, again we will be using a node representation, but here instead of 3 fields, our node will have total 5 fields. So one will be a data field, second left child field, third right child field. So this is as we used before for a simple binary tree representation. Left child will hold address of left child, right child pointer will hold address of right child. But in addition to this, we have 2 more fields to our node structure. So that is struct node pointer left thread and another pointer is right thread. So here what is this left thread and right thread is and what it will store. So to distinguish between normal pointer, that is whether it is a pointer who is storing address of child or it is a thread pointer, 2 Boolean fields are used, left thread and right thread. So these are added to record in a memory representation. So this left thread or right thread will hold value either 0 or 1 based on some condition. So this way your node structure will look like one left thread field, left child which will hold address of left child, then data field which will hold actual data, right child field will hold address of right child, and right thread field will hold either 0 or 1. So for any node P in the threaded binary tree, the left thread is 1. So this is 1. If it is 1, it indicates that left child P is a thread pointer. So that means it is a thread pointer. And when it will be a thread pointer, it will be a thread pointer if it doesn't have any left child. So if it has some left child, definitely it will store the address of that left child. And if it doesn't store address of left child, then it will store null. So if it stores null, that null will be replaced with left thread. Similarly, left thread of P is 0. If it is 0, it means that the left child is present. So if you find it complicated, you can simply look at this statement. This field will be 0 if it has left child, and it will be 1 if it doesn't have left child. Similarly, for R thread, the field will be 0 if it has right child, and it will be 1 if it doesn't have a right child. So again, one example. So this is a given binary tree. All these fields of leaf node, the left and right pointer of leaf node are null, because as they are leaf node, they doesn't have any further child. So for leftmost and rightmost field of the tree, they are dangling or they are null. And for any right child or any right pointer, it will point to Inorder successor of that node. So for H, Inorder successor is D. So right side is holding address of Inorder successor. So for I also, right side is holding address of its Inorder successor. For I, node B is Inorder successor. Similarly for all other nodes. And for left child, it will store address of its Inorder predecessor. For node E, Inorder predecessor is node B. So it is holding address of its predecessor. So ultimately, all these nodes are holding address of their ancestor. So to avoid these, now here we have definitely every time we will be having two dangling pointers, one leftmost pointer and one rightmost pointer, because for rightmost node we don't have its successor, and for leftmost node we don't have its predecessor. So definitely every time we will be having two dangling pointers. So to avoid these dangling threads or dangling pointers, the head node is used in representing a binary tree. So either you can call it as a head node or you can call it as a dummy node, because so you can call it as a head node or a dummy node, because head node is not actually acting as a head node which was used in a circular binary tree or in a circular linked list or any other linked list. So it is not that kind of head node. It is just a dummy node you can consider. And the original tree and the whole tree will become the left subtree of the head node. So see how it will look. So this is your original tree, and this is the newly added head node, or you can call it as a dummy node. As it is a head or dummy node, it is not holding any data. Okay, so we'll come back to this later on. Now just look at this. This is your actual first node or a root node of a tree. Now this node A has both left and right child. So if it has child, it has left child, that means left thread is represented with 0. If it has right child also, then right thread is also replaced with 0. For node B also, left and right child are present. So left and right thread are replaced with 0. For D also, left and right child present, so threads are 0. Now for node H, it doesn't have left and right child. So that means it is a thread node. Now it is not a node which is holding its child data or child address. So it will not act as a normal node. Now it will act as a thread field or a thread node. So here these thread field left and right both are replaced with 1. Similarly, this node I doesn't have left and right child. That's why it is a thread field. So thread field is replaced with 1. Similarly, node E doesn't have left right child. So fields are 1. So whenever it doesn't have left and right child, their fields are represented with 1. So if the field is represented with 1, it will hold address of either its predecessor or its successor. But for the leftmost and the rightmost dangling pointer, we have introduced this head node. So the leftmost dangling pointer will now point back to the head node, and rightmost dangling pointer will also point back to head node. Now in head node again, it has left child A. That's why left thread is replaced with 0 and right thread is also replaced with 0 because for right child it is pointing back to itself. So this is the major change that we need to keep in mind. We need to introduce a head node just to avoid these two dangling pointers so that they will be getting some address to store instead of just null. So that's why head node is introduced, but head node is not actual your data node. That's why data field is 0 and the whole binary tree or a threaded binary tree will act as a left subtree of your head node. So it will be added to the left side of your head node, and for right side it will point back to itself. So this thing you have to keep in mind. So there are few advantages and disadvantages of using this threaded binary tree. So first of all, we'll see some advantages. The traversal operation is more faster than that of its unthreaded version because with threaded binary tree, non-recursive implementation is possible, which can run faster and does not require iteration of stack management. So here, because of these threads available, we have option to traverse in the reverse direction also. So because of that availability of option, we don't need use of recursive function call, and that's why this stack overhead is avoided. We can efficiently determine the predecessor and successor of a node starting from any node. In case of unthreaded binary tree, this task is more time consuming and difficult because in unthreaded binary tree, we can traverse in only one direction from top to bottom of a tree. But in case of threaded binary tree, we have option to traverse in both the direction. Then the disadvantages of this threaded binary tree, the insertion and deletion from threaded binary tree are very time consuming operation compared to non-threaded binary tree because here we have to deal with the threads, that is in-order successor and predecessor. This tree, that is threaded binary tree, require additional bit to identify the threaded link. That's it.